Hey guys, this is Mrs. Harbin, and this is Algebra 1, Section 6.7. We are talking about linear functions, linear equations, and today we're going to look at parallel and perpendicular lines. But first, let's solve with this quick lesson opener. Solve and graph the solution on a number line of 2x equals 6. Well, if we were to solve for x, we know that we would have to divide both sides by 2, and when we do that, we get x equals 3. We're going to show that on the number line with a solid dot at the number 3. What about x plus 4 is greater than or equal to 5? To solve for x, we know that we need to subtract 4 from both sides, and when we do that, we get x is greater than or equal to 1. Because it can be equal to 1, we'll put a solid dot at 1, and because it's greater than, we are going to go to the right. So solid dot at 1 with an arrow to the right. How would we graph negative 3x is less than 12? Well, to get the x by itself, we've got to divide by negative 3. And dividing by a negative switches the sign of everything. It changes our negative 3x to a positive x. It changes our positive 12 to a negative 4. And it also switches the sign in the middle from less than to greater than. So we get x is greater than negative 4. Now, it doesn't say that it's equal to negative 4, so we're going to put an open circle at negative 4, and then go to the right because it does say greater than. If we wanted to check our work, we could pick a number anywhere on this arrow and plug it in. So if I plug in the 0, for example, into my original equation, negative 3 times 0 is less than 12. That gives me 0 is less than 12. That is a true statement, so I know my arrow is going the right direction. Okay, what about 2x minus 5 is greater than 3x minus 7? Well, first we want to get our variables on one side, so you might do that by subtracting 3x from both sides, which would give us negative x over here. And then we need to get rid of this negative 5, so we can add positive 5 to get rid of that, but whatever we do to one side, we do to the other. So we have negative x is greater than negative 2. Well, we're not trying to solve for negative x, we're trying to solve for x. So dividing by negative 1 gives us our final sentence here, our final inequality, that x is less than 2. We did have to flip that sign when we divided by negative 1. Because it doesn't say that it's equal to 2, we need an open circle, and because it's less than, we go to the left. Again, we can pick any value that's on our line and plug it in to see if our arrow is in fact going the correct direction. So I'm going to pick a 0 here. If I go back to my original equation, or my original inequality, 2 times 0 minus 5 is greater than 3 times 0 minus 7. I get 0 minus 5 is greater than 0 minus 7, which leaves me with negative 5 is greater than negative 7. That is a true statement, so my 0 is one of the answers that works. My arrow is going the right direction. All right, the last one I want you to try on your own. Pause the video, try it, and then come back and check your work. All right, hopefully you've done that, and now you're ready to check your answer. You subtracted 4 from both sides to get 3x is less than or equal to 12. You then divided by 3, and you got x is less than or equal to 4. Because it can be equal to 4, we are going to do a solid dot at 4, and because it's less than, we are going to go to the left. Again, let's choose a value on the line. 0 is always the easiest, and plug that in. When we plug in 0, 3 times 0 plus 4 is less than or equal to 16. That leaves us with 0 plus 4 is less than or equal to 16, which is in fact true because 4 is less than or equal to 16. So because this answer on our line works, my line is going the correct direction. That's a great way to check your work. Our biblical correlation for this unit comes from Job 38:5, where God says to Job, "Who marked off its dimensions? Surely you know. Who stretched out a measuring line across?" And this is in the midst of Job complaining to God about all these things that he's going through, and God saying, "Listen, Job, did you do all this? Did you create all this? Do you know who created this? Who measured this?" And we see God mentioning words like dimensions and a measuring line. And that tells us that God is a God of order and precision, and he's got a plan. And we need to make sure that when we are solving problems mathematically, that we are following the steps with order and precision and with a plan. By following the steps precisely, we can recognize patterns and solve the problems that we are going to face in our jobs or in our everyday lives. Our lesson objective for today is that you, the student, will graph linear inequalities. Linear inequalities are similar to linear equations, but they contain an inequality sign instead of an equal sign. Now, at the beginning of this lesson, I said we were going to do parallel and perpendicular slope, but now that I am into the slides, I realize I misspoke. Parallel and perpendicular is a different lesson, so be watching for that video. This one is on linear inequalities. So linear inequalities are similar to linear equations, but they contain an inequality sign. Remember, our inequality signs are greater than or equal to, less than or equal to, or not equal to. So we're going to solve them the same way, just the sign is different. Inequalities do have an infinite number of solutions. If I want to say that my x is greater than 3 and x equals 3 in the equation, I just have one solution, 3. But an x is greater than or equal to 3, I have an infinite number of solutions. It could be 4, 5, 6, 7, 8, 9, 10, all the way up to positive infinity. So inequalities represent an infinite number of solutions. The graph of a linear equation, such as x equals 3 or 2x plus y equals 3, separates the coordinate plane into 3 distinct sets of points. We have x equals 3, which would look like this on the graph, by the way, the Cartesian plane. And then we have this region over here where x is less than 3, and this region on the right-hand side where x is greater than 3. So we've got 3 distinct areas here. In 2x plus y equals 3, we have the actual line, 2x plus y equals 3, and then the area to the left and to the right of that line. Take a look at that on the Cartesian plane. I kind of sketched it on the previous slide, but you can see it here. We have x equals 3. Over here, we've got x is less than 3, and to the right, x is greater than 3. So 3 distinct areas. Let's take a look at what a graph of 2x plus y is greater than 3 would look like. The first thing we want to do, just like when we were solving linear equations, is to solve for y. Okay, we're going to treat it just like an equation, and we solve for y by subtracting 2x from both sides. Just like before, we now know our slope and we know our y-intercept. Our slope is -2 and our y-intercept is 0, 3. We'll then go to the Cartesian plane with that information and we'll begin to graph. Because it's an inequality, not an equation, it does not include the points on the line. Before, if you remember, when we were doing our warm-up, when we had greater than or equal to, we had a solid dot to show that that point was included. And when we had just greater than or less than, not equal to, we had an open dot to show that that point was not included. Well, when we're graphing linear inequalities, like these, to show that a point is included, if it's greater than or equal to, instead of a solid dot, we'll use a solid line. And if it's less than or greater than, if the point's not included, we'll use a dotted line. And in this case, it's not included, so we need a dotted line or a dashed line. All right, so looking at our Cartesian plane here, we know that our y-intercept is 3, so we've got a point at 3. We know our slope is -2 or -2 over 1, so we'll go down 2 and over 1. And we can do that a couple times here, down 2 and over 1, so that we have 3 points for our straight edge. And we will connect the dots with a dotted line. Now it says that y is greater than that line, so we need to shade the area above that line. Okay, again, we can pick a test point here. We could pick like this point right here, 1, 2. And if we plug that into our original inequality, it should produce a true statement, just like we did in our warm-up. When graphing an inequality, remember to solve for y and identify the slope and y-intercept of the corresponding equality. Then graph the linear equation. If the inequality is less than or equal to, use a dashed line. If it's greater than, equal to, or less than or equal to, we'll still use a solid line to show that the points on the line are solutions. Then we'll shade up or down, shade above the line or below the line. If the line is a vertical line, just like in our warm-up, if it's less than, we shade to the left. And if it's greater than, we shade to the right. But if your line is slanted, we'll shade above or below, depending on if it's greater than or less than. If it's greater than, shade above the line. If it's less than, shade below the line. All right, let's try this one. See if you can work along here. The first thing we want to do is get y by itself. To do that, we subtract 6x from both sides, and we get negative 2y is greater than or equal to negative 6x plus 10. We then have to divide everything by negative 2, and because we're dividing by a negative, we are going to also switch the sign here. We end up with y is less than or equal to 3x minus 5. Our slope is 3, and our y-intercept is 0, negative 5. We'll take that information to the Cartesian plane and graph it. Because we have an equal sign here, we know that we are going to graph with a solid line. So let's go ahead and graph that. We said our y-intercept is negative 5. And our slope is 3. Now, if you take a look at this graph doesn't actually match this equation. Do you see what's wrong with it? We've said our y-intercept is a negative 5, but this graph shows a y-intercept at positive 5. Let's go ahead and change that equation so that the equation matches the graph. If we were going to graph that with a negative 5, our graph would be here, and our solid line would look like this. So same kind of slope, just moved over to a different y-intercept. Okay, we're now going to shade. Since the equality sign is less than or equal to, we do need to shade below the line or shade down. Okay, on this one, this is 3x plus 5. On 3x minus 5, we would shade still below the line down here. The only thing that changed is our intercept because of this typo right here, this error. Linear inequalities are often used to model real-life situations in which there are an acceptable range of values. In class, we talked about grades, what an acceptable range of values would be for your grades. And there are a lot of situations in life when you can have an acceptable range of values. The domain and range are often limited to non-negative numbers. Let's take a look at an example 3. This is the same example that you can find in your books on page 271. We're going to let x equals the grams of carbohydrates and y equal to the grams of fats, and we want our total calories to be less than or equal to 720. Our calories from carbohydrates will be represented with 4x, and the calories from fat will be represented with 9y. So to write an inequality, we would say that we want 4x plus 9y to be less than or equal to 720. The first thing that we're going to do when we want to graph 4x plus 9y is less than or equal to 720 is find the y-intercept and the slope. And we do that by solving for y. When we solve for y, we find that our y-intercept is 0, 80. We also know that we want to graph with a solid line because of this less than or equal to symbol. To find the x-intercept, we could plug in a 0 for y, and we find that our x-intercept is 180 and 0. Okay, since we're not going to consume negative amounts, we're only going to graph this inequality in the first quadrant, where all of our values are positive. All right, so if we were to graph this line, we said our x-intercept is 180, and our y-intercept is 0, 80. We'll then connect those 2 points with a straight edge. We're not going to go into the other quadrants of our Cartesian plane because those represent negative values and we can't have negative calories. Then, because it said less than or equal to 780, we need to make sure that we shade below the line. Here we could test this value, 100 grams of carbohydrates and 30 grams of fat. That does equal a calorie amount less than 720, so this does fit into her diet plan. Right, in this lesson, we graphed linear